you've heard the advert, you see the title, go on.
Okay, well, I'm really honored to be invited to speak at the Shimon Eliezer Fest. I haven't known them nearly as long as many people here. I think I met Shimon first around 20 years ago when I was just starting as a postdoc at SLAC, and he was on one of his visits there, and I was immediately impressed both by his very strong physics insight and his extremely friendly nature, very enthusiastic. So I think we had some interesting discussions already then, and thanks to him I visited Israel for the first time because of his invitation, what seems like a very long time ago now. Eliezer I met somewhat later, but actually I read some of his important papers long before I met him, as I'll mention in my talk. So in terms of the subject of the talk, I think Ofer already gave a very nice overview of what has been going on in this field, and I'll probably focus a bit more in depth on some of the subtopics, partly chosen for my own selfish reasons, of course. But first I just want to start with a basic sort of story. Everybody knows why QCD has something to do with string theory. It basically has to do with this mysterious confinement mechanism where when you pull a quark and an anti-quark, a flux tube, a QCD flux tube of some characteristic thickness forms. And we now have very good lattice evidence for why this happens and how this happens. These are actually pictures taken from a supercomputer simulation. So in a nutshell, we want to not just to prove that it happens, but to understand better the dynamics of such phenomena in gauge theory. And here is a kind of movie where a series of images is taken of quark and anti-quark at different separations. And you see that, indeed, the flux tube doesn't really expand. It basically stays of some characteristic thickness of order Fermi. So in that sense, we can say that strings have really been observed, at least on the lattice. And there is strong evidence that they're governed by the non-Bogota area action. Namely, there is a Lucier term comparison, which seems to fit very well the D-2 behavior in 3 and 4 dimensions. But I think beyond this correspondence, which is often known as a kind of effective string or long string description, which is valid when the string is considerably longer than its characteristic thickness, one wants to do something more interesting, I think. Namely, look for examples of exact duality between gauge theory and string theory. And in this context, it would mean that we're not just sort of, we don't just want to reproduce this asymptotic linear behavior of quark-antiquark potential, but we also want to see the nearly Coulombic behavior due to the asymptotic freedom, for example, that appears at very short distances. And here is, again, a picture from the lattice world, which shows this nice transition from the nearly Coulombic to the linear behavior. And I will actually show that although we don't understand QCD, we actually do understand models where qualitatively similar graphs can be made with a lot less computer time. So in fact, my sort of path to search for exact duality started around that same time at SLAC with a paper with Lenny Susskind, which was somewhat different in spirit from this. It more looked for a lattice gauge theory that would reproduce bosonic string in flat space. But this paper was very much based on the light cone gauge transverse lattice formulation of Bardeen-Pearson and Eliezer. So in that sense, I knew of his work long before I met him. And I think this is one of several instances when his work had an influence on me. And then later on, I'll mention a similar instance of Shimon's work, I think, playing a very important role. Okay, so this is a slide that's already appeared many times. It's just basically the idea of large N that has been very important in this. Basically, if you know, in real world, this QQ bar pair creation can occur and the string can snap, but at large n, this process becomes suppressed. So it's certainly easier to study planar theories, these large n theories, but even with planar theories, this idea of direct summation of planar diagrams, suppose we want to evaluate a Wilson loop by some sort of direct summation of diagrams, this has for many years was believed to be out of reach in the four-dimensional gauge theory. And now, thanks to some recent progress, there is actually hope that at least for some problems this summation can be done, and I will review it somewhat later in my talk. But this difficulty with summing planar diagrams made many people drop back to 0 plus 1 dimensional large n models and so on, where we learned a lot, but we haven't yet learned to solve QCD. And then, again, as you all know, somehow there was a return to this idea of gauge theory, string theory duality, which came sort of inadvertently through not so much due to the search for such dualities, but due to much better understanding of the structure of string theory. And in particular, D-Branes, can you read this? Yeah, it's a little bit. Anyways, you all know what's in it, but I'll say it. Basically, so the D-Branes, in some sense, brought string theory back to gauge theory in the mid-90s because they're an efficient tool to realize gauge to embed certain gauge theories in string theories. For example, if we just take the D-Branes and stack lots of them on top of each other, we get the famous maximally supersymmetric Yang-Mills theory in 3 plus 1 dimensions. And this is a picture of a stack of branes. You see that they're defined by open strings that can start and end on each of the branes. So there are n-squared species, just as in UN gauge theory. But then the idea appeared that one should really be comparing this with a certain charged brane object, with a certain extremal charged brane object, whose metrics were already known before then through the work of Horowitz and Strominger. So they're very simple metrics. You have a kind of warped product of the 6 transverse dimensions in the case of 3 brane and 3 plus 1 longitudinal dimensions with a certain this is called the warp factor, and this is just a 1 plus L to the 4 over R to the 4. It's just a green function in 6-dimensional space. So if you draw the picture of this curved space, the idea is that this curved space is created by a kind of heavy stack of branes. And naively, you would say that as you get to close to R equals 0, the 5 spheres surrounding these branes will shrink. But in fact, there is a cancellation of R squared between the warp factor and here. So you develop a kind of semi-infinite throat. And it has the geometry of 5-dimensional anti-de Sitter times 5-dimensional sphere. It's easy to see where the sphere comes from. It just comes from this transverse space. I mean, the space surrounding the 3 branes. So one can start playing games comparing, for example, absorption of external probes thrown at this stack here, or thrown from the asymptotic space at this metric. And one finds basically good agreement in these cases. So one important feature of this particular theory is that in the infrared, when one looks at this theory, one finds this actually super-conformal field theory, which in addition to gauge fields, has 6 scalar fields and fermionic partners. And for future convenience, you can combine these 6 adjoint scalars into 3 complex fields, Z, W, and V. And then what happens is that the asymptotic freedom of QCD is exactly canceled by the extra fields. So the coupling really doesn't run at all. And one can really meaningfully set coupling to a certain value and then study the theory as the planar theory as a function of this value, which is what one of the themes of my talk will be. And then you immediately run into some interesting facts, namely that most observables are really non-trivial functions of this coupling. And for me, the early realization of this had to do with trying to study these stacks of branes at not at in the extremal phase when there is no guess of open strings, but then one can heat them up to a certain temperature or add some excess energy above extremality, which you can think of as some guess of open strings moving on these branes. And then the metric changes slightly, but it's known exactly what it is. And it, roughly speaking, looks like a kind of black hole in anti-de Sitter space. If you can't read these formulae, don't worry. I mean, they're hard to understand anyway. But in a nutshell, you have this. So in anti-de Sitter space, you have this extra dimension, and the horizon basically moves to some position in this extra dimension. Rather than having a horizon, a kind of anti-de Sitter horizon all the way at infinity in this throat, it sort of moves to a finite distance. Okay, so basically this is the metric of this black hole in anti-de Sitter. And then the idea is to identify the Hawking temperature of this black brane with the field theory to which the unequal force superring has been heated. And then, of course, the event horizon will contain the Bekenstein-Hawking entropy, which is just proportional to the area. So then expressing the entropy in terms of the temperature, one finds pi squared over 2 n squared t cubed. So the t cubed is, of course, very nice because it's a signature of a scale-free theory. This is just the Stefan Boltzmann law. And the n squared signifies that there are n squared species. So somehow the geometry really knows that one is dealing with some UN-type theory. But it turned out the coefficient was different from the coefficient one would get in the free Super-Yang-Mills by a factor of 3/4. And initially, this caused a lot of consternation because these were the days when people were used to exact agreements. For example, for Strominger-Vafa black hole, the agreement was exact. But the explanation, which maybe we weren't too clear on initially, is that, of course, there is the coupling dependence. And if one computes in the n = 4 Super-Yang-Mills, not just the free field, but the leading coupling correction, it will correct this coefficient. So there is a whole series of corrections. And then you have to interpret this answer here. You have to interpret this as the strong coupling limit of the function. So there is some kind of sum over planar diagrams denoted by this f of lambda in this case. And what this little gravity calculation gives you is the limit of this function at strong coupling being 3/4. And this is, of course, extremely difficult to check. And to this date has not been checked. But it's essentially the reduction of the coefficient from 1 by 25%. But there are, in a sense, some qualitative checks which we didn't know at the time, but they were developed also in the mid-90s by lattice gauge theorists. It was found that quite generically, if you plot, say, if you take some pure glue theory or a theory with 1 or 2 quarks or something like that, you always, after you cross the deconfinement and go to, say, 3 times Tc, you find that, that the value of the free energy or entropy divided by T cubed, say, is actually smaller than the free field value by something like 20%. And this seems to be quite a generic phenomenon. And now it's actually seems to have acquired some phenomenological significance because people attribute this to really the non-perturbative nature of the theory, even at the temperature several times Tc. Of course, in this case, you know that when you go to a temperature which is 10,000 Tc, because of the asymptotic freedom, you will approach this value. But there is a certain interpolation then, certain curve that takes you from here to a really high temperature, which again has to do with some kind of planar graph summation as a function of coupling. And actually, so this is done for 3 colors, but there was a large N extrapolation attempted by Bringholz and Tepper, which gives you similar results. So basically, large n still has the same effect. But of course, we would dearly love to understand this function and how precisely. And this would be not just, this would be a test of ADS-CFT correspondence, because we just say this prediction is reasonable, but we want to understand it. Okay, so now, so just a few words about ADS-CFT more generally. You already heard this in several talks. You basically have correspondence between string theory and string theory on ADS times some compact space and four-dimensional CFTs. For n equal 4 superring this compact space is a 5-dimensional sphere. Here is again this Escher diagram, which already appeared in Lenny's talk in some form. This shows a space of a negatively curved space, which the ADS space would be after Euclidean continuation, just uniform. Basically, it shows that near the boundary, there is really infinite distance around the circumference of this disk. And the important thing is that, in some sense, you grow this extra dimension, which is z, from this point of view of writing the metric. So from this point of view of writing this Poincare coordinates, the boundary of this space is at z equals 0, and the ADS horizon is at z equal infinity. And then, of course, the reason this is useful is that when the coupling, the 't Hooft coupling becomes big, the radius of the space becomes very large. And then you can do these effective supergravity calculations, maybe with some probe strings and D-Branes added to the game. And this gives you a totally different way of approaching the theory. In particular, you develop expansion and inverse powers of the 't Hooft coupling using higher derivative corrections to the string effective action, while Feynman graphs instead work at weak coupling and develop this perturbation theory in lambda. And this is a typical weak-strong coupling duality. Now it's in 't Hooft coupling. And as we know, in these cases, it's extremely hard to marry the two limits. Often people do two different expansions and then try to patch them together. But lately, amazingly enough, there have been instances where you can marry the two expansions and construct the exact function. And they have to do with, oh no, I was worried about this. I guess it's one of these pesky compatibility issues. But anyway, okay. This is this is lambda to the, yeah, for some reason this is lambda, but okay. Anyway, so just to make this talk less boring. All right, so basically, one thing that we can compare between ADS and CFT is operator dimensions. And in the simple cases, if we know if there is some point-like field or local field in ADS, there is a simple formula for the dual scalar operator in CFT. It's just a square root formula in terms of the mass. So there is a host of so-called protected operators for which the mass is of order 1 over L. And then delta is completely coupling independent. So you can just compare and everything agrees. But these checks are guaranteed by supersymmetry, by the superconformal symmetry. But then there are much less boring predictions. Namely, when you look at the much heavier states, not the supergravity states, but string states, their masses are basically fixed, not 1 over L. And L diverges as lambda to the 1/4. So this makes a prediction that at strong coupling, these generic operator dimensions grow as lambda to the 1/4. And these are much more tricky to check. I mean, if you take some generic operator like Kearney operator phi squared, start expanding it, you will get a couple orders maybe after monumental efforts. But how do you prove that at infinite lambda it goes to 1/4? Well, we still don't know, but we know a lot now, actually. And what we know has to do with some particular example of operators which are highly charged. Namely, one can consider operators which, in some sense, some of them are built out of a lot of fields. For example, there are the Bernstein, Maldacen, and Nastasia operators, which are built of a large number of fields Z, where Z is one of these complex scalars. with a few impurity insertions. I can insert a few W's or a few derivatives. But then there are other type of operators where you can insert lots of impurities. So these operators are highly charged in the sense that they carry a lot of R charge. When you assign charge 1 to Z, these carry a lot of R charge. And in the dual description, this R charge is just the momentum around the 5 sphere. So these are short strings that are circling the 5 sphere. But then, and these are, of course, because they depend on having scalar fields, they're very much a feature of n equal 4, but not of QCD. But then there are high spin operators where you insert lots of covariant derivatives. And these are also present in QCD. They're present in any gauge theory. And in this setting, they're dual actually to strings that elongate within the ADS space. They're just, so these now carry lots of physical spin. And they're important in studies of deep inelastic scattering, which goes back to the work of David Gross and Frank Wilczek in '73. So they have, so we studied these operators about 5 years ago with Steve Gaubser and Sasha Polakov. And we propose that they're dual to actually macroscopic spinning strings, which become very long and sort of stretch towards the boundary of ADS. And then you find something really amusing. If you just compute the energy of the string and identify it with operator dimension, you find a certain logarithm of spin. So just classically, you find that delta minus s, namely the twist, goes like some function of g times log s. And the precise function of g at strong coupling is just 4g. So you get this 4g, and the coefficient is completely fixed by all this ADS-CFT matching. And then somewhat later on, Frolov and Zeitlin obtained the leading semi-classical correction, namely just doing sum over small vibrations around the string, and found that 4g gets corrected by minus 3 log 2 over pi. The next correction will be of order 1 over g and so on. But the beautiful thing is that all these corrections go like log s. And then there are also some gauge theory arguments for why this log s appears actually order by order in perturbation theory. So this suggests strongly that there is some interpolating function f of g. And now we sort of know its form at strong coupling from string theory and at weak coupling from gauge theory. So it's been a bit of a dream for me to marry these two expansions. And this is, seems like a very special observable. So I thought it should be possible one day, but I didn't know it would happen so soon. So how did it become possible? Well, there has been a lot of research in the last 3 years on something called integrability in ADS-CFT. And the idea of integrability is essentially that when you compute the dimensions of these very long operators, the computation you do just in gauge theory can be mapped to integrable spin chains. Namely, if you take an operator built out of many z's and w fields, what happens at one loop is that z and w can get interchanged, but separately the number of z's and w's is conserved. So you find actually that the sort of anomalous dimension operator, which mixes all these different orderings of z's and w's, keeping their number, is exactly the Heisenberg nearest neighbor spin Hamiltonian, which is, of course, an integrable system solvable by beta ansatz. And in fact, this was known to some extent. Actually, it was known in this SL2 case, more important to me in PCD, through the work of Lipatov, Fadeev, Karchemsky, and others already before. But the special thing for n equal 4 seems to be that this integrability survives all higher loop corrections. And this equivalence for the scalar sector was first pointed out by Minahan and Zaremba, and then generalized by Beisert and Staudacher to arbitrary sectors. And then it also seems to be present in the strong coupling description too via string theory. So I think it's a good working assumption that the theory really is integrable. And lately, this integrability idea in beta ansatz, which is a bit too technical to describe in detail, has more or less led to the complete solution of the problem of infinitely long operators. Because, okay, so now it's a square. But okay, yeah, this is pi. So basically, this transcendentality principle is the idea that actually, if you compute the similar quantity in QCD, you find that the term with the leading number of pi's is actually the same as n equal 4 theory. And this is called the Kotikov-Lipatov leading transcendentality principle. They sort of observed it based on their experience with perturbative QCD calculations, and it appears to be true. At least for this quantity, it certainly appears to be true. And this is a pretty striking connection, because it shows that, you know, by trying to compute this in n equal 4, we're really not completely wasting time, even if you're a very experimentally minded person, because you're computing completely accurately a term in a QCD quantity. Okay, but then there was a question of how does f of g behave at 4 loops and beyond. And here, dramatic progress took place due to the efforts of basically, there were 2 very important papers by Beizert, Hernandez, and Lopez, and Beizert, Id, and Staudacher, who essentially determined the scattering of magnons along the spin chain defined by these operators. Essentially, if you think of these W's as impurities, you can scatter them off of each other, and this is dictated by some exact S matrix. Beizert showed that this S matrix is determined up to a phase, this phase being some complicated function of the coupling and momenta. But amazingly enough, these papers present us with a formula for this phase. And then this formula can be used to derive an equation that determines f of g, an complicated integral equation, which I'll call the BS equation, the Beizert and Staudacher equation. And this equation, for example, it makes definite predictions to all orders. And for example, at 4-loop order, it makes this prediction. You see that zeta of 3 squared appears, and pi to the 6 with certain coefficients. And these both are assigned the same transcendentality, because zeta of n is assigned transcendentality n. So these are both transcendentality 6. And then, so the question is, can one check this perturbatively? And it turns out that, just a bit of history of what was happening over the last couple of years, it turns out that Byrne, Dixon, Chacon, Kassauer, and Smirnov actually set out to use their fancy unitarity techniques to compute precisely this coefficient. And some people thought that the fate of ADS-CFT correspondence was hanging in the balance there, because a previous version of the prediction had a minus sign here rather than plus. And if they found the result agreeing with the minus sign, then many people would conclude that ADS-CFT is wrong. In fact, I heard many such talks, and their argument was that this would mean that a certain integrable system with a trivial phase would be correct, at least up to 4 loops. And that would be, and who would ever worry checking the 5-loop answer? Okay, but some of us certainly thought that at 4 loops something different would come in, and it did. But the remarkable thing is that these guys computed the answer numerically, but accurately enough to be able to guess that you just have to flip this sign. So they arrived independently at the same conjecture for the perturbative expansion of f of g. And I actually, in my spare time, sometimes try to guess how to continue these coefficients. But I can assure you that not even with the wildest imagination you would be able to guess this. So you get like proliferation of zeta of n factors. You get arbitrary number of zeta of odd coefficients multiplied together. And these guys, using this BS equation, you can generate a 117-loop answer for you and so on. And now only up to, So the for loop has been tested, but only numerically. And now there is a more accurate method of Kashaza-Spradlin-Valovich, which confirms this answer to very high accuracy, but they still can't do it analytically. So if you will, this contains an infinite set of predictions for QCD, not just for n equal 4, but for QCD, because it's the leading transcendentality answer. But then the question remained whether the strong coupling limit of the function dictated by this BS equation agrees with the string prediction, which let me just go back to. So this is a string prediction, 4g minus 3 log 2 over pi. And then there was a perennial question of what happens in between. What if ADS really gives you some answer totally unrelated to gauge theory, right? There was always such a question. And here, luckily, I think there is no problem at all. In fact, so we solved this BS equation numerically, which turns out to be a highly accurate method of finite matrix truncations. And you find that apart from this little, so you know that near 0 it's going to go smoothly as g squared, but for large g it has to go linear with some intercept. And you see how rapidly it approaches extremely rapidly the string prediction of the linearity. And just from numerical fits, we could see that this is minus 3 log 2 over pi. It works to many, many significant digits. Of course, it should be possible to do the analytic solution, but this has been accomplished to leading order. So this 4g is now analytically established, but the higher powers are very difficult to do analytically because integral equations tend to be hard to solve. But a bunch of people are now working on this. There is also a very interesting exercise of a two-loop comparison, the 1 over g term, which hopefully will happen. But already at this level, you see how well this extrapolation works. There is absolutely no singularities in between. And that I think certainly is a remarkable test of string theory, not in laboratory, but via n equal 4 super Yang-Mills and integrability. Okay, so now I want to switch gears to another topic, which is confining gauge theories. I may have to skip some of the things. And Ofer already talked quite a bit about confining vecchia. But so besides solving n equal 4 super Yang-Mills very precisely, which we see also has some relevance for QCD, one wants to understand more general gauge theories. So there is a sort of general question of how the strings fit into this game. And if you look at the picture I initially showed, you would say that you need confinement to get string picture. But here you get string picture even for a conformal theory. And this is because of this fifth dimension. What happens is that the QQ bar potential is computed by a string that bends into the fifth dimension just right to give you an exactly Coulombic potential. So from here, you know that if the metric is sort of nearly ADS near the boundary, you're going to get nearly Coulombic potential at short distances. But then, as Ofer already showed, if you go to large Z, which is the infrared in the gauge theory, you can get confinement if space comes to an end, kind of, at large Z. And then what the string will want to do is sort of lie down at the end of space and gives you confinement. So these two behaviors kind of can be matched together, and you really do get nearly Coulombic at short distance and linear at large distance, just like in QCD. And one example where this happens is something that I've been working on for many years, maybe too long, called the warp-deformed conifold, where you really can get both the near ADS behavior in the UV and confining behavior in the infrared. And it's given by, so it's a theory which is engineered on a more complicated stack of branes than just D3 branes. You also need some wrapped D5 branes. But when dust settles, the dual background is actually very simple. It's in the transverse space, you find a Calabi-Yau metric called the deformed conifold, which is known analytically, warped by just a single function as a function of a radial coordinate. and the same warp factor enters into the 3+1 dimensional warping. So, and the interesting thing is that this appearance of a deformation of the conifold is really a sign. It happens due to the fluxes that that are sourced by these branes, and it's really a dual gravity demonstration of dimensional transmutation. So you can really see the dimensional scale generation from gravity. And the way you see it is, actually, we saw it sort of in real time. Because the painful history was that before we realized that one needs to add this epsilon squared on the right-hand side, we were just playing with the undeformed conifold and found a solution with Zeitlin which had a naked singularity. So it had good features in the UV, but in the infrared it had a naked singularity signified by 0 of the warp factor. And this was actually sort of string theory telling us that something went wrong, because when the solution is singular, something went wrong. And then we realized that what was missing was basically chiral symmetry breaking. And this chiral symmetry breaking in this case is implemented just by adding this one parameter epsilon here. And in this case, it's completely unique because there is a 3-form flux which wants to blow up a 3-cycle within this cone. And there is a unique sort of deformation which singles out this 3-cycle. And after this deformation was taken into account, the warp factor became completely monotonic and had just the right features to make the string fall to the end of space, which is here tau equals 0. And this way, you get an acceptable solution with chiral symmetry breaking. And this chiral symmetry breaking is exactly of the Veneziano-Yankelevich type. It's exactly of the same type as in supersymmetric gluodynamics, which was a very important guide for us, actually, once Strassler and I started thinking more carefully about what's going on in the infrared. So this finiteness of the warp factor at r equals 0. So here there are 3 cases. One is the conformal behavior, where this warp factor blows up, the unacceptable naked singularity, where it goes to 0, and the confining behavior, where it monotonically approaches a finite value. So in this case, I would say it's a kind of via string theory. You can really prove confinement in this type of gauge theory. And this gauge theory is, in the UV, it's rather complicated, but it has the nearly conformal behavior. Rather than approaching a fixed point, it has a so-called cascade behavior, which I basically don't have enough time to explain, but one needs to understand Seiberg duality to really become, to understand this behavior. Essentially, what happens is that the theory at any scale is something like SUKM cross SUK plus 1M, but then it undergoes Seiberg dualities along the flow until in the infrared it reaches, roughly speaking, SUM super Yang-Mills. And for that reason, it exhibits the same pattern of chiral symmetry breaking, Z2M down to Z2. And this Z2 is very easy to see because before we added epsilon, there was essentially arbitrary phase rotation of this conifold equation, sum of z squared equal to 0. But once you add epsilon, all you can do is just change the sign of z. So all that remains in the infrared is just the Z2, which is exactly as predicted by the Veneziano-Yankelevich superpotential. So this appearance of epsilon is really a must from all points of view. And it is the confinement scale. So all the string tensions and blue ball masses in this type of theory are proportional to this epsilon to the 2/3. So this is a dimensionful parameter in the theory. But in fact, something actually somewhat more interesting happens in the infrared, because it's perhaps more correct to think about the last stage of the cascade as this SU2M cross SUM theory, where the SU2M gauge group actually has an F equal NC. And this is the special case which, as explained by Seiberg, has quantum deformed moduli space. And in particular, one can write down 2 baryon and anti-baryon operators, A and B, made out of certain fields in this gauge theory. So if you look more closely, this gauge theory has bifundamental fields A1 and 2, B1 and B2. And out of them, you can construct baryons. And it turns out that this very solution actually has vacuum expectation values for these baryons. So the baryonic symmetry present in the Lagrangian is actually spontaneously broken, which leads to the appearance of Goldstone boson and its superpartner. So it's perhaps more like QCD than we originally thought, because it actually has something like a pion, but it's a pion coming from the closed string sector rather than from the mesonic sector, which is pretty bizarre. But actually, I have to credit Offer for emphasizing to us that this Goldstone boson really has to be there for consistency, and it was extremely hard to find initially in the supergravity spectrum. But eventually it was found. And moreover, one can even go to finite distance along this baryonic branch. So in the gauge theory, you know that there is a whole moduli space of confining vecchia labeled by the webs of these baryons. So this C, this zeta is the baryonic branch modulus. And through some really monumental effort of this group, Buti, Grania, Menassi, and Petrini, and Zaffaroni, they constructed solutions for finite distance in the moduli space along this baryonic branch. So instead of just one confining theory, we have a whole moduli space of confining theories, and we can compute things like string tension along this moduli space. And the key idea is that this fundamental string at the bottom of this throat, which I like to call resolved word deformed conifold for technical reasons, is really dual to this chromoelectric flux tube. Okay, so another amusing thing is that instead of just seeing indirect evidence for these baryon vacuum expectation values, one can really compute them using a Dirichlet 5 brane, which wraps the entire Calabi-Yau space. And this was again guided by the work of Offer, who pointed out that the wrapped D5 branes at infinity are really dual to these baryonic particles. And then when one thinks about how a one-point function is computed, you really have to take this whole D5 brane and smoothly extend it in the interior. So it's really it's a very natural object. It's a Euclidean D5 brane wrapping the whole Calabi-Yau. And from its action, one can really unambiguously conclude that there are one-point functions for these baryons. And these can even be computed as a function of this modulus Xi. Okay, so all of this gives us a exact solution and a certain limit of 4D large N gauge theory with pretty rich dynamics. And at least it should be a good playground for something, for testing various gauge theory concepts. And for example, some results on global spectra are already available. And while the global spectra are essentially computed from just, if you go back to the picture, all the global wave functions are localized in the infrared near the tip of the conifold. And in principle, one just needs to compute the spectrum of fluctuations around the solution. But it's a very technically complicated task because there are lots of fields turned on and fluxes. So it's something that has been going on for years, and still only partial results are available. But as mentioned by Offer, perhaps the most audacious hope is that somehow these models could provide some bridge to physics beyond the standard model and cosmology. And one example of this is this idea of Kachru, Kalash, Linde, Maldacena, McAllister, Trivedi, which is that if you take this sort of warped throat that I described and glue it into some compact Calabi-Yau space, then this serves as the basis for the so-called KKLT model after you have added the anti-D3 brane at the bottom to break supersymmetry. But then one can insert a D3 brane and think of its position as an inflaton. And at least naively, you get a pretty flat potential, so you might be able to inflate. And while you may think it's a pretty weird model, by now this paper has hundreds of citations, so lots of cosmologists have studied this. It doesn't mean that it works, but in fact, there are definite fine-tuning issues with these models, and we've actually, with our group in Princeton, with Bauman, McAllister, Maldacena, Demarsky, and Murugan, we tried to compute some issues related to corrections to this inflaton potential, and generically these corrections tend to spoil flatness, but it's very interesting to see how to compute these corrections and so on. But it's widely viewed, at least as the most promising D-Brane, anti-D-Brane inflation model, and perhaps it can be made to work. So this type of modeling, where you really think of these type of throats as a way of generating physics beyond the standard model, might be probably the best hope for literally these type of spaces. And within the space of flux compactifications, these type of conifold warped throats appear to be quite generic, because conifold is the most generic sort of local Calabi-Yau singularity, and if you add these fluxes that I have added due to these type of D-branes, then this conifold kind of elongates. So you take this tip, and kind of the fluxes tend to pull out this region, as shown in this picture. Of course, in reality, it's a very butchered picture, because this cone itself is 6-dimensional, and you also have 3+1 dimensions of our world, but at least it gives some kind of inspiration to look at these. Yes? Oh, these are polarization. This is the WMAP3, where but I think they don't have too much significance yet on polarization. Okay, so let me conclude. As we all know, his string theory was really born through attempts to understand strong interactions, and somewhat unexpectedly, over the last 10 years, this string gauge duality has become, again, a preoccupation for many people, because ADS-CFT correspondence does make some very precise predictions for behavior of strongly coupled gauge theory. And very recently, this incredible progress due to exact integrability and beta ansatz has really allowed to not just to make predictions about strong coupling behavior, but to really start with weak coupling and continue and match them to the string behavior. So they give precise tests of string theory in ADS space, and would be interesting to know what other examples of this sort can be solved. Because to find the solvable non-supersymmetric quantity, even in a supersymmetric gauge theory, is pretty remarkable. So as I told in the second half of the talk, extensions to confining theories provide new geometrical understanding of various important phenomena that we expected to see, but now translated into this huge geometrical language, such as dimensional transmutation, chiral symmetry breaking, appearance of Goldstone bosons, and so on. So this certainly offers some tantalizing hopes that perhaps QCD can be solved along this route. And it could perhaps arise at the bottom of a warped throat, which is somehow akin to this particular warped throat. I think in reality it's going to be strongly curved, probably, but that's sort of the picture that this suggests. But of course, there is much work to be done, because understanding string duals of weakly coupled gauge theories is difficult. And then, but perhaps the most intriguing possibility is that these type of models that arise in gauge string dualities can explain something about new physics that we don't know about yet, like, say, inflation or hierarchy beyond the standard model. Okay, so I've basically come to the end of my talk, and whenever I prepare talks, I always think about this recent finding due to cognitive psychologists. Actually, it's not a recent finding, that apparently in each session you come away with 7 ± 2 bits of information. And so I always try to limit myself, but not very successfully, sort of like at lunch before this talk. So I realize that there is much more than the 7 bits. In fact, the person who discovered this used to be my neighbor, which is why it's always on my mind. Okay, so I don't know which lessons, which 7 bits you'll carry. Hopefully it's 7 plus 2 that you'll carry from this talk, but I think certainly the most important message is this one. It's happy birthday to both of you, and I'm using the same picture from the conference webpage, but I recently heard a rumor that about the history of this picture, that these 2 notorious boundary dwellers actually, in this case, were somewhat beyond a certain boundary. So I wish both of you to continue crossing boundaries, and many happy returns of this day. Thank you. Thank you, thank you. No, yeah, I think the deep and elastic scattering has been studied, and yeah. Yeah, what happens? Exactly. Yeah, what happens is that as you crank up the energy, you kind of things tend to go towards the boundary, towards the UV. I mean, it's really this 5th dimension that enables you to see both the short distance structure and the long distance structure all in one kind of setting. So I think it's again these extra dimensions coming in. But here, for these models, you really have to carry all 10 dimensions, and they all play a very intricate sort of role altogether. But people are convinced that you need at least 5. I think one is yet to see a really, a 5D model on the same footing that these 10-dimensional solutions are. But they might exist. I mean, it's just.
These guys, it used to cost $1 million for a computer, and now they've moved to 10 million. The next iteration is 100 million. The next iteration of that will probably be impossible. Can we get rid of them?
Well, I don't know. I take a more positive. I think they've given us lots of clues, and I think for real-world QCD, I don't see at the moment any hope that we can put them out of business. But there are some, I think the example that people cite is if one finds certain special quantities that the lattice gauge theories just cannot compute. For example, the viscosity of this plasma. For the free energy, as I showed, they can compute it, and ADS is qualitatively in the right ballpark. But when it comes to transport coefficients, the Euclidean simulations just nobody is promising anything at all. But say at the Rick collider, they're measuring indirectly the viscosity. So that's where things come in. I think, as always, I think these sort of more theoretical subjects in physics, their value is maybe not so much to provide the exact solution, unless in some really special cases like asymptotic freedom, but just to provide a kind of qualitative view, and in that, I think it's already been noticed by lots of QCD people. So I would say it's on the map with QCD people. It hasn't reached the status of the solver of QCD, but it's done good things for both fields, I think.